All right, so we are going to go over the basics of intermolecular forces. There are three main ones that we're going to talk about. We're going to go from weakest to strongest. Okay, so here we go. Intermolecular forces, really easy concept. Okay, inter means between. Okay, so you're talking about forces that deal with kind of how molecules interact. Okay, so we're talking about how molecules are actually interacting with each other. So different molecules are interacting with each other. And there are, two basic ideas, right? So you either have repulsion forces or you have attraction forces, which is pretty basic. Hopefully we all understand that, right? Repulsion, so any two things that are the same, basically, will always repel each other. So like negative will repel another negative, a positive will repel another positive. Okay. Attraction would be opposites attract, right? So negative is going to be attracted to a positive. All right. And again, we're talking about how two different molecules are interacting with each other. So, of course I have these because I'm a nerd. Okay, but you're talking about like not the forces within the molecule itself, not the bonds within the actual molecule. Okay, we're talking about how two molecules would either be attracted or repelled from each other. Okay, so how these two dudes are going to interact. All right, and intermolecular forces are much weaker than intramolecular forces. Okay, intra just means like within. So the forces that are holding an actual molecule together, so like the covalent bonds or the ionic bonds that we've already learned, these dudes are much stronger than the intermolecular forces, talking about how one molecule interacts with another. All right, pretty basic so far. So there are three main types, and again, we're going to go from weakest to strongest. Okay, so the weakest dude, number one, weakest, all right, is part of a van der Waals, AALS force, and we call this a London Dispersion Force. Okay, yay, big words. All right, so I actually love one of the ways that this was explained to me way back when, and I'm going to try and do that for you now. Okay, so basic idea, okay, is you have this lovely like farm, okay, and you have this pen or a pasture, and in the pasture there are a bunch of sheep. Okay, stay with me, I promise it'll make sense. Okay, so at some time the sheep might be totally evenly spread throughout the entire pasture. Okay, they are completely even, everything's nice and aligned, yay, but they're sheep and they don't stay like that forever. I can't control exactly where they are. They're moving at any given point. I can't ever tell exactly where all the sheep are at one point. So more realistically, I'm gonna have some sheep be huddled on this side. Who knows? Maybe because they're sheep, they're looking over here at something. I don't know. Okay, but the sheep are moving around the pasture. They are not going to be evenly dispersed. Whatever, you get the idea. I don't need a million sheep. Okay, so at any one time, the sheep might be huddled over on this side. At another time, they might all migrate to over here. At another time, they might be evenly dispersed again. Okay, they're moving around. The sheep can move. Sometimes, again, they're all nice and even, but when they're not, and there's a higher concentration of sheep on one side, you get what's called the London Dispersion Force. Not with sheep, but with electrons. Okay? So in any atom, okay, doesn't matter which one, pick an easy one. Let's pick neon, okay, because that only has 10 electrons to deal with, so it's relatively small. Okay, I have my 2 electrons on the inside shell, on the first shell, and then I have my 1, 2, 3, 4, 5, 6, 7, 8 electrons on my second shell. Okay, imagine there are shells there, if they actually stayed in nice shells. Okay, so sometimes the electrons are all nice and evenly dispersed. Sometimes they're not, right? Sometimes these electrons, because they're zipping around every which direction, they are not going to be evenly dispersed. Okay, so sometimes your neon's going to have your 2 inner electrons like maybe off to the left, and maybe you have more of a concentration of electrons up over on your left-hand side again. So yes, it's still, I mean, the atom itself is still electrically neutral, right? You still have as many protons as electrons. Nothing has changed there, but just where the electrons are kind of changes how the atom feels, if you will, okay? So this side of your neon atom will kind of feel, bear with me, negative, right? It feels slightly negative because more electrons are over there. This side, where there's less electrons at that given moment, will feel positive. Okay, and we call this a momentary dipole. Okay, dipole, new exciting word, not confusing. Di means 2. Pole, like north and south pole, right? Opposites. So you've got 2 kind of sides, if you will, of your atom or your molecule if you're dealing with a bigger entity, okay? And we use this very fun symbol, delta, but instead of the big triangle for like a capital D, this is a funny little, it almost looks like a musical symbol if you guys play music. Okay, so you get a delta minus, so a partial negative, or a delta plus, so a partial positive, and this is momentary. So the thing about van der Waals, a couple of key important pieces. Number, throw that away. This is again London dispersion. All right, thing number 1. All right, for London dispersion, this exists in all molecules. Okay, so every single one will have some kind of London dispersion force because electrons are moving around, and I cannot control exactly where they are. Makes sense. Okay, it's also momentary, which we talked about, and it has a bigger effect for heavier atoms. Okay, which hopefully makes sense because the heavier the atom, or the larger the atom gets, the more and more electrons there are, so the more electrons that can be kind of gathered on one side. All right, so again, this is the weakest of the 3 that we are going to talk about for Gen Chem, okay? So London dispersion, van der Waals, weakest type of intermolecular force. All right, number 2, which is your kind of medium strength, is called a dipole force. Okay, so this we need to kind of sort of review electronegativity, which hopefully you remember anyway, but just to be sure, okay? All your electronegativity values are on the bottom of your periodic table, okay, or the bottom of every single element of your periodic table. It's listed, and I just printed up this one so you can see it color-coded and you don't have to like zoom in and look at the actual numbers, okay? But on your periodic table that's given to you, you have the electronegativity numbers of every single atom that's on there, okay, element. So basic idea of electronegativity, right? The more electronegative you are, the more able you are to attract electrons, right? So which one is the super attractive element? Whichever one is able to attract more electrons. So the things that actually want electrons, like fluorine, chlorine, oxygen, these guys have a really high electronegativity because they want an electron. The things that really don't want electrons, like anything in your alkali metals, most alkaline metals, right? These guys don't want electrons. They want to get rid of electrons. They have very low electronegativity. So low on this scale is purple, high electronegativity is red. Okay, so the more electronegative you are, the more able you are to pull electrons towards you. Okay, and this creates something called a polar molecule. Okay, and again, polar, like you have poles, right? You have a north pole and a south pole. There are poles. So one pole of your atom is going to feel more negative because you have a more electronegative element. For example, okay? I drew beautiful pictures for you, okay? If I have hydrogen bonded to chlorine, so this would be like hydrochloric acid if we dissolved it in water, okay, or hydrogen chloride. If we look at this lovely picture, right? Hydrogen's kind of in the middle with his electronegativity. Chlorine is red, okay? He is one of the most electronegative elements. So chlorine wants the electrons more toward him. He is going to be able to pull those electrons and attract those electrons that are within the covalent bond between hydrogen and chlorine. Chlorine's going to pull them towards him. Okay, greedy little guy. So instead of the electrons being shared like evenly, like exactly between hydrogen and chlorine, they're not. They're actually going to be much closer to chlorine. Okay, this guy goes away. Okay, so the electrons that are within your covalent bond are much closer to chlorine. Okay, so the way we actually draw this, we draw this with a little arrow with a cross. Okay, so it's like, which direction are your electrons being pulled? They're being pulled towards chlorine. Okay, and I actually really like the way that we draw this symbol because it shows you this side where the electrons are being pulled away from kind of has like a positive sign. Okay, and your electrons are going towards chlorine, so this side is going to be your more negative side. And same exact thing, we draw a delta minus on your chlorine pole, right, the pole of that molecule, and we have a delta plus on your hydrogen. The hydrogen feels more positive, the chlorine feels more negative, just because it's more electronegative, okay? Another example of this would be like ammonia, okay, NH3. You can always look on your periodic table, okay? So nitrogen, one of the most electronegative elements, okay, he's orange. Hydrogen's, again, green, right? So nitrogen is going to pull on the electrons that are being shared between nitrogen and hydrogen. It's going to pull those electrons more. So, right, all of these electrons from the shared covalent bond of hydrogen and nitrogen are being pulled towards nitrogen. So this side of your molecule feels negative. It has a partial negative charge. And this side has a partial positive charge. Okay? Very exciting. This would be exactly this, right? So your electrons between your hydrogen and nitrogen are being pulled more towards the purple. There's less negative charges on this side where the hydrogens are. So this side of your ammonia would feel positive. This side where nitrogen is feels negative. Okay? All right. Basic rules for creating a polar bond or actually having a polar molecule. Okay, so you need a difference in your electronegativity that is greater than 0.4. So you can double check on your periodic table because all of the numbers will be given to you, okay? You need a bigger difference than 0.4, all right? So a good example of this would be carbon and hydrogen. So if I had like methane gas, okay? Yes, technically carbon and hydrogen have different electronegativities. However, carbon's electronegativity is 2.55. Hydrogen's electronegativity is 2.20. This is not greater than 0.4, so we would consider them to be the electrons within these covalent bonds to be shared relatively equally. Okay, so this would not be a polar molecule. We would call this a non-polar molecule. Both of these dudes would be polar. Okay, so far so good? Of course. The other thing for another nonpolar would be if you had the exact same element bonded to itself, right? There's not going to be one element that's pulling on the electrons more because they're the same element. They have the same pull on those shared electrons. So this would also be nonpolar. There's no dipole. There's no side that is partially positive or partially negative. All right, so that's that. If I have a dipole-dipole intermolecular force, that means the partial negative side of one element is going to be attracted to the partial positive side of another element. So your elements will kind of line up in a very specific and unique way so that their partial positives and partial negatives are attracted and their partial positives and partial positives are repelled. Let's see if I can... Okay, we'll use these waters for later, but they'll be at least good to help us now. Okay, so oxygen, much more electronegative than hydrogen, right? Oxygen is one of the most electronegative elements. Hydrogen in the middle, okay? So the oxygen side is going to feel more negative. It's the partial negative part of your water, okay? So this oxygen side feels negative. It is going to be attracted to the hydrogens, which feel positive, of the next water. These hydrogens that are partially positive will repel the partial positive of the other hydrogens of another water molecule. So this water molecule will kind of rotate and orient itself so that the positives and negatives are kind of lined up. Okay, same thing here. Like your oxygen is going to be repelling another oxygen. They're both negative. This dude will reorient itself, which makes sense, right? Positives are attracted to negatives, not the other way around. Okay, so that was a dipole-dipole. And our last intermolecular force, number 3, which is the strongest, okay, is called hydrogen. Let's spell hydrogen correctly. Bonding. All right, and fun fact, hydrogen bonding is a dipole force. It's just on steroids, okay? So it is the literal strongest type of intermolecular force. It is a dipole-dipole, but it's specifically dealing with hydrogen and 3 other molecules. So it can have an oxygen bonded to a hydrogen, a fluorine bonded to a hydrogen, or a nitrogen bonded to a hydrogen. Okay, so any of these dudes will result in what's called hydrogen bonding. All right, and again, we'll pull out our lovely waters. Okay, so, right, the oxygen feels negative. Hydrogens will feel positive, partial positive. Okay, and your water will orient itself so that the hydrogen from one water is going to be attracted to the oxygen of the other water. So they are going to be held tighter together. It's an intermolecular force that is very attractive, very strong. Okay, so same thing. This oxygen has a delta negative. Okay, my other water molecule here is going to kind of like rotate around until the delta positive sides of my hydrogen are facing that oxygen, right? Because my oxygen that's negative is going to be attracted, oh, but this didn't stay down, okay, to the hydrogen, going to be attracted to the hydrogen, okay? It's hydrogen bonding. They're very much attracted. I mean, you get the idea. I don't need to put down 7 million waters for you, okay? But this hydrogen is going to be attracted to the oxygen. So hydrogen bonding is actually ridiculously important, especially dealing with water. It is one of the reasons that water has such a high boiling point. We'll talk about that in the next video or two. We're talking about special properties of water, but hydrogen bonding is incredibly important, okay? Again, it's just a dipole-dipole. It's just a really strong dipole-dipole, okay? Dealing with polar molecules. And you have to have one of these 3 types of bonds within your molecule, okay? All right, that's it. Intermolecular forces, 3 of them, okay? Van der Waals with a London dispersion force, that's the weakest. You get dipole-dipole, which is medium, and then you get hydrogen bonding, which is a type of dipole-dipole, but super strong. Good luck.